Hey guys, this is Barbara Garcia. I wanted to go over a little bit about your periodic table, chapter 2. Again, just so I know that we did it in class last week, but it was very rushed. So I just wanted to make sure that we get it a little bit better and are able to stop, rewind, and listen to it again if we need it. All right, so what I want you to remember is, so for example, up here is hydrogen. And over here is helium. Remember that these two are in a row together. What this means is anybody that's over here on this row means that they have full valence shells. Okay, so remember that we have protons, and protons are positively charged. Yes, protons are positively charged. We have neutrons, which have zero charge. Right? And then we have electrons, which are negatively charged, okay? Right? So remember, the protons and the neutrons are usually found in the nucleus, in the center, and the electrons are going to be found floating around in valence, in shells. The valence shell is the outermost shell, okay? So for example, hydrogen. Hydrogen, if you take that little box and you kind of make it big, right? You'll see that hydrogen is going to have a number of 1, and then like a weight of 1.008, okay? And so what that means is it has 1 proton. Protons weigh about 1 atomic mass unit. So if it has a 1 in it, that's all it has. Protons and neutrons usually weigh 1 atomic mass unit. So again, all hydrogen is a proton in the middle, okay? And whatever number of protons an electron, a atom has, is going to have an equal number of electrons. So if it has 1 proton, it is going to have 1 electron, unless otherwise stated. If you see this with just your hydrogen ion, that means that the hydrogen ion has lost its electron and the only thing left is the positive proton. Okay? Now, why would hydrogen do that? Hydrogen can do one of 2 things. In order to fill its shell, notice that this one has 1 over here, and then this one has a 2. Okay, so that means that the first shell, the first electron shell is going to be filled with 2 electrons. So the next shell is going to be 1, 2, 3, 4, 5, 6, 7, 8. So the next shell is going to be 1 above that, just like I drew over here. Now, if hydrogen, in order for it to be happy, needs to have a full valence shell. So it either has to, in its normal natural state, which means it has 1 proton and 1 electron, it needs to pick up 1 other electron to be happy and to be full. In other words, it cannot exist just like this. So most of the hydrogen that's in the atmosphere, for example, is going to be H2. That's hydrogen gas. Okay? And what is that, right? It has 1 proton. There's 2 of them. And then each one has an electron. And they're sharing an electron in what we call, right, a covalent bond. Okay? So when you share electrons, that's called a covalent bond. So hydrogen gas, this is hydrogen gas, all the way around our universe, there's a bunch of hydrogen gas. Hydrogen gas is a diatomic molecule, 2 hydrogens. Each one has 1 proton in the middle. Each one contributes 1 electron. Together, they are sharing electrons. So now, because they're sharing electrons, that shell has 2 electrons because they're shared. So the electrons will be floating around here and will be floating around here equally. And so sometimes we can represent that as a line, right? Like this. So sometimes you'll see it represented as a line. Often you'll see, for example, carbon represented in a line like that with hydrogen, okay? Especially in our carbohydrates. Our carbohydrates are very heavy in carbon, hydrogen, and oxygen, okay? So, right, so carbon. Carbon, if you look over here, okay, carbon has 6 protons, okay, and it has a weight of 12. 0.00, I think it's 001. Maybe 01 without another 0 in there. Okay, so what does that mean? That means that carbon has 6 protons, right, positively charged. It has 6 electrons, okay, and it's going to have 12 minus 6. It also has 6 neutrons. Neutrons are going to be denoted by that, okay? So a little 0 with a line through it, okay, because that means they have no charge. In the nucleus, it's going to have 6 protons, 6 neutrons. Means that the net charge of the nucleus is positive. Then the electrons are floating around. But how do they float around? Okay, they're going to be floating around, right? So you have the nucleus with its 6 protons and 6 electrons, which I'm not going to draw. Then there's first shell. The first shell is full because it has 2 electrons. Then the second shell of carbon has 1, 2, 3, 4. And you know this because it's 1, 2, 3, 4. It has the 4th position. Okay, the 4th position means it's going to have 4 electrons in the outer shell. All of these are going to be exactly the same. All of them are going to have 4 on their outer shell. Okay, so their outer shell, for carbon, it's the second one. For, tin, it's going to be the 5th shell. But all of them will have 4 electrons on that outer shell. Okay, which means they need to get 4 more in order to be happy. Now, carbon, what it does is that it does a lot of this covalent bonding in order to gain those electrons. So you'll often see carbon in a carbon-hydrogen bond. Carbon always makes nonpolar bonds. Nonpolar bonds. Okay? Because the electrons are going to be floating around all of the different elements equally, right? All of the different elements that are attached are going to be equally sharing those electrons. So there's no partial charges. However, water, for example, does carry like a partial charge. The reason water carries a partial charge is because oxygen, okay, oxygen is a very electronegative element. Nitrogen, oxygen, and fluorine, bromine, and iodine, and everybody else on here, which don't worry about those, they're not in our human body. They're going to be very electronegative. Why? Because they only need, for example, anything on the column where fluorine is located, okay, they are all going to need only 1 electron in order to be happy. Okay, since they only need 1 electron, they are highly electronegative, which means they're going to attract a lot of those electrons so that they can have full shells. So I want you to notice that chlorine often is not just going to be chlorine, it's going to be existing as chloride, which means it added an electron. Think about this as an inventory. The inventory states that you are going to have 1 more electron than you have a proton. So chlorine normally has 17 protons. If it's chloride, which means now it's happy, it is going to have picked up 1 more electron. So now it is going to have an outer shell. The 3rd shell is going to be full with its 1, 2, 3, 4, 5, 6, 7, 8 electrons. We call that the octet rule. Okay, so the octet rule is going to be when we fill in all of those different shells, the outer shell especially. Okay, now chlorine is going to have a negative charge. Okay, because chlorine has a negative charge, it is not, in this case, it's not sharing an electron, but it could be sharing an electron. Like sometimes it will be sharing electrons with different things. However, most of the time, what it's going to do is it's going to have what we call an ionic bond, not a covalent bond. A covalent bond is bonds that you see in, for example, peptide bonds are going to be a type of covalent bond in which they're sharing electrons. Sometimes they're sharing equally, sometimes they're not. That really depends on what the are the two elements that are in that sharing that electron. If is nitrogen or oxygen, the likelihood is that it's a polar bond. Okay, so I'm gonna talk about that in just a second, but we got into chlorine, so let's talk about chlorine for just a minute. I'll get back to polar bonding and water in just a second. So chlorine is now going to exist as chloride, which means it picked up one electron, and now it has a charge. We call that an ion, right? And that's why we make ionic bonds, because there are certain elements that are either going to give up their electrons or they are going to get electrons. All of them on here will always be picking up electrons because of their electronegativity. Electrons are going to be attracted to the electronegativity of these elements. Okay, so they will always exist as ions, like chloride. And we call them chloride, bromide, iodide. That's the name that we use, right? Fluoride. So they're always going to be existing with an extra electron in nature. We're not going to see them without that. Now, because they have that one extra electron, now they have a charge, right? So now they're charged, they're ions. If it has a negative electron, it's called an anion. If it has a positive one, it's going to be called a cation. So, for example, hydrogen, like I mentioned before, it can do covalent bonding with another hydrogen or with a carbon, where it can get its one extra electron to be happy. However, it can also give up its electron and function as an ion. So if it's functioning as an ion, it gave up its electron, a hydrogen ion, which, by the way, hydrogen ions are what we measure in pH, is hydrogen ions. Okay, so for example, hydrogen ion, yes, is going to have a positive charge because it gave up its one electron. Hydrogen will never ever exist as an H negative picking up an electron. No, it's either going to have a covalent bond or it's going to give up its electron. It's just never going to be H negative. It's only going to be either H positive or in a covalent bond. So if it is H positive and it comes near something called, chloride with a negative, they're going to be attracted to each other. That's called an ionic bond, right? So then when they come together, they form HCl. For example, HCl is something very commonly found in our body, right, called hydrochloric acid. It's the acid that's in our stomach, right? So hydrochloric acid. And hydrochloric acid can be very, very strongly acidic because when in water, these dissociate into the positive hydrogen ion and the negative chloride ion, and then that contributes to the amount of hydrogen ions in a solution, and therefore whenever you have extra hydrogen ions in solution, a lot, you're going to be more and more acidic. Okay, so remember, acidity is going to be based on the number, and so the number gets lower. So the more acidic it is, the more hydrogen ions there are, the lower the pH number. Okay, so pH is the negative log. So as the number of hydrogen ions increases, the number we give to us as acidity is going to be lower. So if you're, for example, super high in hydrochloric acid, you're going to have lots and lots of hydrogen ions. The closer and closer you're going to be to a pH of 1 or even a pH of 0. It could be less than 1. All right, so again, hydrochloric acid is going to separate in water. Okay, and I can tell you a little bit about why water does that in just a second. Because I'm going to tell you a little bit about the polar bonding in water. All right, so also hydrogen ions give up their electron. It's in the outer shell, and then they're only a proton. Okay, so sometimes you'll hear hydrogen ions just called a proton. Any of these in this column are also going to function exactly the same. They're called the alkali metals. They all function exactly the same. Okay, they are going to have, for example, lithium. Lithium has 3 protons, 3 electrons. The first 2 electrons are going to be found on the first shell. That first shell is full. Then it has 1 electron on the second shell. In order for it to be happy, it would have to pick up, right? It has 1, 2, 3, 4, 5, 6, 7 more electrons to have a full second shell. That's not going to happen. Never, ever is lithium going to pick up 7 electrons or any other of the alkali metals. They're never going to pick up 7 electrons. So what they do is they give up that 1 electron, which then reverts back. So an empty valence shell reverts back to the shell before it, which is a full shell. So for example, lithium, sodium, potassium, rubidium, cesium, and everybody else in that list, which none of these are important in the human body, but sodium and potassium are very important. They're always going to exist as ions. They're going to be cations, Na positive, K positive, okay? And you know that because they're positive, they're going to be attracted to things that are negative, like, I don't know, chloride, right? So sodium, chloride, super important. You know that they exist as salt. That's an ionic bond. That ionic bond is going to be disrupted by water. I'm going to tell you about that in just a second. Now, looking at this second column, you have calcium, right? Calcium is going to exist as 2 positive. Also magnesium, okay? Why? Because they have all of these in this column, right, are all going to have 2 electrons in the outer shell. So, right? So remember, this is 1 electron. This one has 2. That's helium has full valence shell. Helium is a noble gas. It will not react with anybody. It's not wanting any bonding. It does not want or need any electrons. It is happy just the way it is. Same thing with neon. But neon has, right? Notice it says 10. It has 2 in the first shell, and then it has 8 in the second shell. It is perfectly happy like that. Okay? Everybody else is going to either have electrons or are going to give those electrons up, or they're going to acquire more electrons either by sharing electrons or by electronegativity and pulling electrons off of something else. All right, so magnesium and calcium, they have 2. Again, they need 6 more to fill up their shell. Never going to happen, right? The alkali earth metals, all of them are always going to give up their 2 electrons, and they're going to live their most stable life as an ion. This is an ion with a 2+. So for example, calcium with a 2+, which means it's given up 2 electrons and it has 2 more protons than it has electrons, is going to like to coexist with something called phosphate. Phosphate has 4 oxygens and a phosphate, and it's 2 negative, which means that it has 2 extra electrons. So 2 positive and 2 negative, they like each other, right? Doesn't that seem obvious? And then they're going to make a crystal called hydroxyapatite, or the calcium phosphate crystal. That is our bones, right? Our bones are made of that hydroxyapatite crystal. And you know, sodium and chloride make another type of bond. They make an ionic bond. They make a different type of crystal because it's sodium and chloride. Potassium chloride can also make another type of crystal. So I don't know if you've ever seen that. I know they sell it as salt, like for your filter and stuff like that. Okay, for filtration systems, right? So hydrochloric acid, very, very acidic because it has the hydrogen ions. Remember, pH is measured by the concentration or the number of hydrogen ions. The more ions you have, the lower the number. Okay, so that was my little spiel. Now let's get to talking about water. Water is very special because water utilizes oxygen. Oxygen is very electronegative. Over here, oxygen has a 6, right? And it has a 16. Well, it's like 15.9, so we put like pretty much 16.0. Okay. I'm sorry, not a 6. It's an 8. Apologize. It's an 8. Carbon is a 6. Now, it has, and this is where I got confused, it has 2 electrons on the inner shell. And then on the second shell, because remember, it's on the second row, that means it has 2 shells. If it's on the third row, it has 3 shells. If it's on the fourth row, it has 4 shells. The outer shell of oxygen has 6 electrons. So which means it needs 2 more electrons. But oxygen, so while it needs and it can get 2 electrons to share, like it does with water, okay, the problem is that because oxygen is so electronegative, it does not share the electrons equally. So the electrons are always floating around the oxygen molecule, rather than going around, remember that these things are all attached, right? So it's an oxygen, right, that's going to be attached to a hydrogen ion. Okay, let me try to draw you a little picture of that. I'm going to try. Right, so it's an oxygen. Remember, that's the nucleus, which I'm not going to draw, but the nucleus has 8 protons and 8, remember, that's a 16, so 16 minus 8 is 8 neutrons. On that first shell, oxygen has 2 electrons. On that second shell, oxygen has 1, 2, 3, 4, 5, 6. Okay, so 6. So what we do is we're going to get a hydrogen, which provides 1 electron, and then another hydrogen providing another electron, right? And now you're going to have oxygen with its 2 hydrogens, and that forms water. All right? And now, the electrons are supposed to be floating around these shells, yes? But they don't float around equally because of the electronegativity of oxygen. Since oxygen is so highly electronegative, it is not going to have that. It's not going to have that ability. So highly electronegative, all the electrons are going to float around it. So what happens is that this creates a partial charge. So the partial charge is going to be a partial negative charge. Partial negative charge. And around the hydrogen ions, right, since the electrons never go around there, well, rarely, right, they are only going to revert back to the proton in the nucleus. So it has a partial positive charge. Okay, so partial. So these are called partial charges. This little symbol is the delta symbol. And that just is a symbol for partial charges, okay? So water is polar. These are polar covalent bonds. They are sharing. They're just polar bonds. But the fact that water is polar is like the whole reason why we exist, okay? Because of the polarity of water, when it makes bonds, it arranges itself based on its polarity. So when you have like a drop of water, it has like a gajillion, millions and millions and millions of water molecules in it, right? So the water molecules are all going to arrange themselves in a particular orientation where you're going to have, okay, so this is another water molecule that I'm drawing over here, okay, where you're going to have the hydrogen ion with its partial positive charge kind of lined up with a oxygen with its partial negative charge, because they're charges, they're attracted to each other. Just like the sodium with the positive charge that has the one more proton than an electron because it gave up an electron, because that one has a positive charge, and the chloride, which picked up the extra electron, has a negative charge. Those are full charges. Those are ionic bonds. They are full charges, but these ones are partial charges. So it's more of an attraction, right? So they're attracted to each other because of a partial positive and partial negative charge, right? Remember, the oxygen has the partial negative charge. So because they're attracted to each other, they make a different type of bond. This is in between water molecules. So this is one water molecule and this is another. So in between, we have, noticed that I drew it with a dashed line. Those are called hydrogen bonds. And hydrogen bonds are actually really important because you'll see them not only between water molecules, but you'll also see them between things that have a lot of nitrogen, like some amino acids. Remember that proteins are made up of amino acids. That's also in chapter 2, right? Proteins are made up of amino acids. Those are the building blocks of proteins. Proteins have a primary structure, secondary structure, tertiary structure, and sometimes a quaternary structure. The primary structure of proteins is going to be the sequence of amino acids. The sequence of amino acids is going to be determined by DNA. That's the whole purpose of why DNA has a particular sequence of letters, is so that the sequence of letters that it has is going to denote the sequence of amino acids that are going to be derived from it. So DNA, remember, goes to RNA. RNA is going to make proteins, right? So DNA to RNA was transcription. RNA to protein is called translation. So we're translating it into a sequence of amino acids. So every protein is going to be built by the blueprint that you have in the nucleus of every single cell in your body called DNA. Okay, so that's the primary structure. Some amino acids are polar because they have nitrogen or oxygen. Some of them are non-polar. There's 20 different amino acids. About 8 of them are non-polar, and pretty much all the rest of them are polar. Okay, so if some of them are acidic and some are basic, so they're either non-polar or they're polar. So the ones that are polar are going to be attracted to other ones that are polar, and so that polarity again is going to be created by partial bonds. These partial charges. So because they're partial charges, you're going to have hydrogen bonding being the secondary structure of proteins. Secondary structure of protein is beginning what we call the three-dimensional structure of proteins. Three-dimensional structure of proteins is going to be determined by the polarities and the way that those polarities of different amino acids are arranged. If your DNA is messed up, it could be that you code for the wrong amino acid. If you change a polar amino acid to a non-polar amino acid, this is exactly what happened in sickle cell. You're going to lose the ability to make a bond. In the case of sickle cell, there is a hydrogen bond that is supposed to be created to keep the three-dimensional structure of hemoglobin correct. Hemoglobin is incorrect in people with sickle cell anemia. So because it's incorrect, does not have the right polarity, can't make a hydrogen bond, that's then going to cause the cell to sickle because of the shape of the protein.